So now we will see that suppose we have features F1 and F2 and we have the output or label. So F1 suppose and F2 are categorical. Suppose F1 has values like low, high, and F2 may have certain values and the output may be 5, 6, 7, 8, 9. Now what we'll do is, if we need to select the decision sequence, it will be done based on the sequence having highest information gain. So suppose we have done that, we found out that feature 1 should be the root. Now feature 1 has the types low or high. Okay. Now what we can further do is, here since the output is numerical, first of all, this entire data set is present at this node. Okay, this is present at this node. Now you find the mean of all these values. The mean of this column, that will be 7. Now, the labels that we used to have here used to be yes or no. And then we used to find out here how many yes or no are there, here how many yes, no are there, here how many yes, no are there, we used to find. Now, the label is no longer a value, but it is a condition. Here we'll have the labels like mean of this greater than 7 and mean less than equal to 7. Okay, mean greater than 7, mean less than equal to 7. In this particular data set, sorry, not mean, value greater than mean, that is right here, 1 second. Value greater than mean and value less than equal to mean. We know that mean is 7. So which values are greater than the mean? 7, and which values are less than the mean? So here mean is 7. Now this entire data set was present over here. Now wherever there is low, that time it will come in this left subtree. So we'll redraw the data set here. And here also. So here F1 should be low only. So low, low, low. We have 3 examples where F2 may be something and output is 5, 7, 9. And here F1 is high only, some value, and output will be 6 and 8. So we have got 2 subsets of the data set based on whether F1 is low or high. Now what we need to do is, we need to again calculate the mean of these values. Mean of these values will be what? Let us calculate. 5 plus 7 plus 9 divided by 3. So it will become 19 divided by 3. So whatever this value is, 6.1 something, whatever it is. This is the mean now. Mean of the left subtree. So here, again, instead of labels like yes or no, we have the conditions that whether the value is greater than mean, that is 6.1, or whether the value is less than equal to 6.1. Based on this, we will have the number of labels. So now, again, we need to split further. From this node, we have found out the labels, the values, how many are greater than mean and how many are less than mean. So here, the number of values which are greater than 7 at this low. See, here we have found out number of values which are greater than 7, we need to find out. So how many there are such values? Number of values greater than mean equal to 7. There is one such value. and values which are less than or equal to mean equal to 7 are 2. That means 5 and 7 and 9. Okay. So initially, the number of values which are greater than 7 are 2, and number of values less than equal to 7 are 3. Okay. Before splitting the feature into low and high, at the feature node, we have 2 values which are greater than 7 and 3 values less than equal to 7. Now, on splitting into low and high, we found subsets. In these subsets, how many values are greater than the mean? 1 in this left subset, only one value greater than the mean, that is 9. Here we have 5, 7. So 5, 7, and 9. Now, in this particular subset, there is only one value which is greater than mean 7, that is 9. So I've written 1. And in this subset, there are 2 values which are less than equal to 7. So I've written 2. Okay. Similarly, for high, here number of values that are greater than 7 and number of values less than equal to 7. The number of values greater than 7 are 1, less than equal to 7 are 1. Okay. So at this particular split, both the labels, that is v greater than 7 and v less than equal to 7, are of equal probability. In such a case, we have seen that entropy is 1 and Gini index is 0.5. Okay. So this is a completely impure split, this one, because entropy and Gini index are at their maximum values. Now, we have done this. Now, further, at L and at H, considering these data sets only, what we have to do, same process, what was that? Find out the mean of all these values, which comes out to be 6.1 something. So, further split this data set into, we have to select which category. Maybe again, we can split using F1 or using F2 this time. So, suppose F2 has the values like A, B, B, A. Suppose we want to split as per F2 now. So I'll write here F2 and we split this as per A and B. Now, how many such cases are there? Out of this, I'll write down the correspondingly here also. When it was 7, it is B. And when it is 9, we have A. And here, when we have high, it is B and high it is. Now, whenever F2 is A, we'll get this particular data set, L, A, 9. And whenever F2 is B, we'll get, here again one was the L, A, 5. And here it will be L, B, 7. Okay. So based on this, we know that initially we had one value which is greater than the mean, 7, and 2 values which are less than equal to the mean, 7. Now here, again we need to see that here number of values which are greater than the mean 7, we have 1, number of values greater than 7, 1, and number of values less than equal to 7, we have 1. Okay, see here, we have 1 greater than 7 and 2 less than equal to 7. So 1, 1. Now there is only 1 remaining, that is less than equal to 7. So here value which is greater than 7, we have 0 such values, and values less than equal to 7, we have one such value. And we know that summation of all these values should be equal to summation of this end. So here total is 3, and here 1 plus 1 plus 1 is also 3. Okay. I hope this much is clear. Similarly, on the right hand side, we can see that number of values greater than 7 and number of values less than equal to 7. So here we need to do the same way. So I'll do it again separately for the high on a new slide. So I've rewritten things a little clearer. What we did first step was we took the data set in which features are numerical, categorical, and the label is numerical. We found out the mean of all the numbers in the output. The mean came out to be 7. So we considered the labels as values less than 7 and values greater than equal to 7. So we have written those labels over here. Now we need to find out in our data set how many values are greater than the mean. There are 2 values. How many values are less than equal to mean? There are 3 values. Now feature 1 has the possible values like low and high. So we made the subsets of the data set accordingly. Now we know that here total examples are 2 plus 3 equal to 5. When they go into the left and right branch, this number 5 should remain constant. That means the summation of this is 3 and summation of this is 2, and 3 plus 2 is equal to 5. Okay. So this is how we have reached till here. Now, what I said earlier was the same thing I'm explaining. Do the same process for this particular data set now. Same process means which process? The process that you did on this particular large data set in the beginning at F1 node. So what was the process? First to calculate mean. Mean of 579 is 6.1 something. So the labels now will be values greater than 6.1 and values less than equal to 6.1. Okay. So how many values are greater than 6.1? We have 7 and 9. So we have 2 values. And values less than equal to 6.1, we have 1 value. Now do the splitting based on suppose feature 2 we say. Then feature 2 when it is equal to A and feature 2 when it is equal to B. So we'll have the subsets of this data set. Ka subsets will be these. So whenever we have A, we'll write those particular sets. Whenever we have B, we'll write that particular set. Okay. Now we'll check whether the consistency is maintained or not. In this particular A, how many values are greater than 6.1? We have 1 value. And how many values are less than equal to 6.1? We have 1 value. Here, how many values greater than 6.1? 1 value. And number of values less than equal to 6.1? 0 value. So 1 plus 1, 2 plus 1, 3. And here also 2 plus 1, which is 3. So consistency maintained. So whatever process I have explained till now, that means first select the feature, best feature was splitting. Add that feature, find how many values are greater than mean and less than equal to mean. Then you divide based on the types of values that that feature has. Then you'll get subsets. Then you can check how many values are greater than 7, how many are less than 7. If the values here are only of one type, means all the values are greater than 7 and the values less than 7 are suppose 0, then it is a pure split, you don't have to split further. But suppose the values are not like that, that means here there is 1 and here there is 2. Then maybe you want to split further. In such a case, you will have to use this data set and find the mean, number of values greater than the mean, less than the mean. And then another feature you consider, subsets of that. Again, you find the mean and so on. Now, what is a parameter to consider in order to find stopping the splitting? One feature, how will you stop the splitting? The stop criteria. One is whenever you get a pure split. Pure split means what? When entropy is equal to 0, Gini index equal to 0. Okay. Another hyperparameter. Hyperparameters are the parameters which you can manually set in order to suit your application or as per your requirement. Another stopping criteria is MSE, that is mean squared error, which is calculated by the formula 1/2 number of training examples M. Summation of differences between predicted and actual value. This is what we did in linear regression also. This is the formula to calculate mean squared error and a square of these differences. Mean absolute error will be what? In which instead of taking square of the difference, you take absolute value of the difference. That means instead of square, you'll simply take absolute value and you won't square it. So if mean squared error or mean absolute error is decreasing as you traverse down, and means as you're going deeper and deeper in the decision tree, if the mean squared error or mean absolute error is reducing, then you at a certain value of that MSE or MAE, you can stop. Okay, this is another parameter. So it is a bit confusing for the first time, but try to work on it, try to dry run for greater depths. Okay. So this was about the decision tree when you have such splitting criteria. Now let us summarize all the possible cases of decision tree. So firstly, we have seen when our feature is categorical and our label is also categorical. Then the possibility is feature is numerical and label is categorical. Then feature can be categorical with label numerical, or feature can be numerical with label as numerical. So here we have seen all 4 cases in which we'll take a particular feature. For this particular case, we select one feature and it has categories like C1, C2. Initially, the labels are suppose yes and no. Then if number of yeses are 5 and number of no's are 4, then here after splitting the labels yes and no will be what? Maybe they are 2 and 3, and here yes and no are 3 and 1. So that when you add all of these, it comes out to be what? Number of yeses comes out to be, number of yeses is 2 plus 3, that is 5. Number of no's comes out to be 3 plus 1, that is 4. That means these should be retained. Right? This was when feature and label are categorical. Now, when feature is numerical and label is categorical. So when feature is numerical, what we have seen, we'll select a particular feature. Then whenever values are greater than, suppose the feature has values like 2.1, 2.5, 3, 6.1, and so on. We'll select each of them one by one. Then we'll select this one, this one, this one. So suppose we have selected, we are at 2.5. The number of values greater than 2.5, number of values less than equal to 2.5. Okay, these are our branches now. And then here label may be yes or no. Here find out how many yes, how many no. Here find out how many yes, how many no. So the main idea is that in the features, if there are numbers, find it out for conditions where each and every number is tried. If the features are categories, then definitely write the categories over here. So this is when labels are categorical, feature can be categorical or numerical. Now, then the label is numerical only and feature can be categorical or numerical. Now, features are categorical means what? Suppose we select F1, we have C1 category and its C2 category. And the labels are now numerical. So what do? We find out the mean of all the labels, and then we'll find out how many values are greater than that mean and how many values are less than equal to that mean. These are the two labels now. Okay, conditional. We are using conditions in place of the actual labels because labels is now numerical. This is the way to do it. Then based on this, how many values are greater than, how many values of the data set are of C1 and are of C2. Means in the data set where all F1 is equal to C1 and where all F1 is equal to C2. Those subsets will get here. Then we can verify that how many values in this subset are greater than the mean M, same M, and how many values are less than M. Right? So just now we have seen this previous video. Similarly, now the case is when the feature as well as the label is numeric. Now what you do, your labels will be value greater than mean and value less than equal. And what will be your features? Your features will be, you'll have to try each feature one by one. So if F1 has the values like 2, 3, 4, 5, 6, you will find out whether it is efficient to split the value greater than 2 and less than equal to. With these labels, you'll try out for this particular splitting. Then if you'll try out for this particular splitting, taking 3, then taking 4, and so on, and you'll find out the efficient value to be selected. And then once you finalize, suppose this particular condition, then you'll get subsets. And here, how many have values greater than M, less than M, right? So this case, when feature and label both are numerical, is very expensive, right? So I hope you understood all these. Now I'll also run one example and show you. This example was executed by Krish Naik, who has a YouTube channel. So I'll show it to you. So here, this is an example of running decision tree. So initially, we need to import pandas as PD, matplotlib.pyplot as PLT. Then from sklearn, we will import the iris dataset. Now, either you can give the path of the CSV file, and using pandas, you can import the dataset. Or sometimes Seaborn and sklearn and some other libraries have inbuilt datasets. Means within these libraries, datasets are available. The CSV files are available. So from them, we are importing the dataset iris. So in iris dataset, we know that we have features like sepal length, sepal length, then petal length and all. And the labels can be virginica, versicular, or setosa. Types of flowers based on their petal length, sepal length. So this is the dataset. Then what we need to do is, we need to import the decision tree classifier. Like how we used to write from sklearn dot linear model import linear regression. We used to import for linear regression problem statements in this way. So for decision trees, what we need to do from sklearn.tree, instead of linear model, no longer linearity, we are using tree type of data structure, import decision tree classifier. Then we create an object of this class. And by default, the splitting is Guinea as mentioned earlier. Then we need to fit this. So initially we are setting the figure size also, because when we build our model, we can actually print the decision tree. And those figure size we are setting in the plot, we are writing figure size to occupy 15 row size and 10 column size. And now this tree, we need to plot. Okay, so it is decision tree classification. That is why tree.plot.classify is written. And filled true means certain values you'll get to see on building the decision tree. So after doing it, after plotting the tree for the classifier, so the object name was classifier, we fit the data, we have trained it. Now we are plotting the tree that it has generated internally. So this is the tree. As you can see, we have a particular root node, then splitting, right? You can see some values over here. We can see the Guinea index. By default, Guinea is used. So here Guinea is 0.5. If Guinea is 0.5, means probability is equal for both. And here Guinea has come out to be 0, means one kind of labels only. So further splitting has not been done, as you can see. We continue with this particular split and so on. Here we are reaching Guinea 0, that is pure split, so we are no longer splitting further. Then Guinea is not 0, so we are splitting further. And so on, this tree is constructed. Now remember, here Guinea is coming 0.6 or something initially. Why? Because we know that the labels that we have for iris dataset are Virginica, versicolor, and Setosa. So this is not a two-class classification. This involves three classes. If there are two classes, then Guinea index will have values from 0 to 0.5. There are three classes, it may be above 0.5 also. Okay, so this has been plotted. Okay, so this was all about decision trees. A little confusing or complicated as compared to linear regression. However, this is the most preferred because almost all the use cases or problem statements are successfully solved with the help of decision trees. And another difference between decision trees and linear regression, when to use, you can also understand by data visualization. Suppose these are two graphs and you have the data points somewhat like this. Then you can understand that we can draw a straight line. Best fit line can be predicted. But suppose the values are like this. That means there's no linearity between these values. That time we can consider the splitting. Why? Because suppose this is the petal length or whatever it may be, then petal size less than 2.0 and greater than 2.0. We'll split it over here. So we can find out this region. Then maybe from here we can split this way. We can find this region. And so on splits can be done. So if there's no linearity or if there's a disconnection between the displayed data points, then we can say that we have got a decision tree to be used. Okay. So now we have seen decision trees. In the first practical, as per the syllabus, we are going to use random forest. Now, what is the connection between trees and forests? We know that a forest is a collection of trees. So whenever we use random forest algorithm, it internally uses a collection of decision trees. That means whatever we have seen just now for us creating a single decision tree, which is quite expensive at times, this will be done multiple times for each of the number of trees considered in the random forest. So that is used in ensembling technique. Random forest uses ensembling technique, which we'll see later. Thank you. So now we will be using ensembling techniques. There are two types of ensembling. One is bagging and the other is boosting. Now in bagging, we have the algorithm called as random forest. Random forest is an algorithm, machine learning algorithm, supervised machine learning algorithm, which uses the technique called as bagging. Then algorithms which use technique called as boosting are AdaBoost, gradient descent, and XGBoost. So in this video, we are focusing only on bagging since we are interested in random forest algorithm. Now what bagging does is, suppose we have a data set D, which has B columns and A rows. Now every time we'll take a certain set of rows and a certain set of columns, or you can say certain set of rows and certain set of features. Each time we take, suppose, this particular section of the data set, then we'll take this particular section, another section, and another section. So now this section which you have taken of the data set, called a subset of the data set, is suppose D. Then other subset is D dash, other subset is D double dash and D triple dash. Why dash I'm writing? Because D is not equal to D dash and D double dash are not equal. Means each of the subsets are not equal to each other. This is because each time we select a subset, we are doing row sampling and feature sampling. Row sampling means that suppose we take X rows over here, X1 rows, then we'll take the next X2 rows, then we'll take the next X rows, say X3, and the next X4 rows, X3. Means some of the rows we'll replace, some we may not replace as well. For example, if we have the rows A, B, C, D, E, then maybe in the first set we'll take ABC, in the second set we'll take CDE, in the next set we'll take BDE. Means we'll take randomly some set of rows. Similarly, we will take randomly some set of values, some set of columns. So randomly we'll take set of rows and some set of columns. If we are taking randomly some rows, columns, means suppose AB will take, then BC will take, then AC will take, and so on. That means row sampling with replacement of rows, feature sampling with replacement of features. So suppose we are taking A1 rows and B1 features, A2 rows and B2 features, A3 rows and B3 features, A4 rows and B4 features, wherein some of the rows and features may be same or different in each of these subsets of the data set. Now these subsets which you have taken, they are actually fed to some kind of model. Some kind of model, that means some kind of algorithm will work on each of these subsets. Which is that algorithm which will work on each of these subsets? It is nothing but decision tree algorithm. Will work on each of these subsets of the major data set. And whatever output we get, that means the prediction that the label is yes or no in case of categorical label. Or if the label is numerical, then whatever the output is, which numerical value should come. As we go on splitting, we understand that which particular value should come, which particular value has highest probability of occurrence. So that value will be given. After applying decision tree algorithm on each of the subsets, we'll get some output from each of the decision tree. Now, suppose it is classification decision tree, that means decision tree classifier. Then suppose we are getting the output as 1 and 0, or maybe yes and no. So at the end, we need to combine all these values, which are the outputs of each of the decision tree algorithms. And in classification, we will take the majority of all these values. It is called as voting algorithm, maximum voting algorithm. So voting algorithm, in which we'll take majority of all the outputs, which we have 1, 0, 1, 1. The majority or the maximum occurrence is of 1. So the final output taken from this particular data set is said to be 1. This is how random forest works. Okay. So this is how random forest will work. Now, in case this is a classification algorithm, if this was classification, then we would get some particular output over here. Suppose this was classification, then suppose we are getting the values like 2, 3, 4, and 5 as output from each of the decision tree regressors. Then when it is regression, we have to take the mean of all outputs. So we will take 2 plus 3 plus 4 plus 5 divided by 4. So the mean will come out to be 3.5. So this is how decision tree regressor will work in terms of random forest. Now, certain notes about this particular method. It will have low variance, and initially when we apply random forest, note that this decision tree algorithm will work individually on this subset. This decision tree algorithm will work individually on this subset. This is algorithm on this subset and on this subset. So the decision trees, as we know, provide overfitting as one of the characteristics. So these outputs are after well training based only on this subset. So the outputs that we get are an outcome of the very good training based on only this subset. This output is the outcome of very good training on this subset, right? So how can we say that when we are working on subsets, based on the output that we are getting by working on subsets, how can we call that output to be the output of while working on the entire set, right? We have not worked on this entire data set as a whole. We are working on subsets of the data set. But you may be, this is what the thought may come to you. But you know that we are applying row sampling and feature sampling. Means what? Randomly we are taking rows. Even if the data is sorted over here, maybe low values are at the top, high values at the bottom. But we are taking randomly some set of values. So not necessary that we are taking all the low values in one set, all the high values in another set. No, we are randomly taking. Also, columns are being taken randomly. And we are taking the mean in case of continuous output and the maximum or the majority in case of classification output. Hence, you can say that it will work fine even though we are not working on the data set as a whole. Now, Suppose this is our data set, which has 1000 rows. Suppose some of the 200 rows, or maybe only the last 200 rows are changed. Then what will happen? Due to row sampling, feature sampling, these 200 rows will get equally distributed. These 200 rows will get equally distributed in all the subsets. Hence, maybe 2 rows will go here, or maybe 50 rows, 20 rows, whatever, how many ever rows will go here. That is why this change that is done has been distributed almost equally in all of the subsets. And that is why our output that we get over here will not change by a great amount. Output will not change by a great amount. That is why the random forest decision trees, they work very well on most of the data sets, right? Now, whenever we work on a separate data set, one of the data set, it will provide something called as low bias. Because while working with one particular data set, we may develop the decision tree up to a great depth. That means it is well trained on this subset, but when we go for testing, that time its accuracy is very poor. If you give a particular example from the training data set itself, it will work very well. But if you give some new example from the testing data set, it will not work well. So on the training data set, you are working very well. This is called as low bias. But on the testing data set, whenever you work, you'll get high variance. High variance means lots of disparity, unevenness, or you can say lots of difference, not uniform, high variance. That means based on the testing, you are saying that yes, my model is giving the exact correct output. This is because of overfitting. Once you go to the testing data set, model is not working good at all. That is called high variance. Okay, so low bias is related to training data set, high variance is related to testing data set. But as I told you, since we are taking random sampling of rows, we are doing row sampling and feature sampling randomly, and we are taking the mean or majority of the output. That means our change is getting distributed, and hence it will work well on testing data set as well. That means high variance will get converted to low variance, which we want on the testing data set. So this is what we'll use in random forest in our first practical. Thank you.